Oh, okay. So I saw the recording button come on. So I guess so Francois, I'm assuming we're good to go with recording.
Yeah, no, that's fine.
Excellent. Good. Okay. We're gonna go ahead and kick things off. So thanks everyone for being here. We have this is one of the if there aren't very many benefits to having virtual seminars as opposed to face-to-face seminars. However, one of the awesome benefits of having virtual seminars is that we are able to hear talks from around the world and aren't tied only to presentations that can be given by people who can get to Raleigh, North Carolina. And today is one of those days where we have a presenter who we might not have been blessed enough to have grace our seminar this year had it not been for the pandemic. So I guess if there's a silver lining, there it is. I would like to introduce this week's seminar speaker, Francois Van Gerden. Is it Van Heerden, Francois?
Van Gerden, no, it's correct.
Okay, good. So Francois Van Heerden is a scientist in the radiation and reactor theory section at NESCA, and as some of you may have guessed from the conversation prior, NESCA is located in South Africa. So it's fall right now, so the colors are starting to change. I guess you were saying early fall, getting there.
Yeah, it's still very early. Yeah.
Okay. So Dr. Van Heerden has a PhD in mathematics from Utah State University, which he received in 2004, and he joined the Radiation and Reactor Theory group in 2007. His particular areas of work include transport code development, as well as the continued development of pre- and post-processing platforms, which facilitate multi-code and multi-physics support within the OSCAR 5 code suite. So with that, Dr. Van Heerden, the floor is yours. We will have questions at the end, and of course, we'll have either a combination of chat room annotation and people raising their hand at the end of the seminar. So with that, I hand the floor over to you.
Thank you so much, and thank you very much for this opportunity. Let me just see if I can start the screen share. Okay. Okay, can everybody see that?
Yes, looks good.
Okay, thank you. So I will be talking about the OSCAR 5 code system, which is our in-house developed suite of codes. Kind of the history of it, where we are going with it, what its current capabilities and status is. Now, okay, there we go. So just the outline, I'll give some introduction and background, introduce the platform itself, talk a little bit about the data model, the application workflow, how we actually use the system to perform analysis calculations, our current status in terms of multi-physics support, quality assurance, what is the development process for and distributing the code, verification and validation session of the code, and then finally some concluding remarks. Okay, just so where I'm from. So as was mentioned, I'm from South Africa. We are actually located on the Pelindaba site. That's that picture here in the upper right corner. I mean, that's the reactor building right here. So our building sits right next to it. It's actually, unfortunately, just off the picture, but it's here in the corner. Where I'm from the Radiation and Reactor Theory section, which is within the Research and Technology Development Division of NEXA. NEXA, by the way, stands for South African Nuclear Energy Corporation. I don't think there's no place where it's explicitly stated. So our group provides operational support for the Safari 1 research reactor. I'm not giving a lot of information about the reactor, but that's a 20 megawatt plate type MTR material testing reactor. It is kind of operated on a continuous schedule and is heavily involved in molybdenum production. OSCAR development is another part of our focus, so that is our nuclear reactor simulation package. We also provide expert nuclear analysis services using the system in broader areas and to the broader nuclear industry within South Africa. So reactor analysis, criticality, shielding, and activation. Okay, so on to the introduction. Like everybody knows, as a modern nuclear reactor analysis incorporates a wide range of computational tools and methodologies. Making use of the advances in modern computing architecture, so many high-precision simulation software packages are now freely available, focusing on isolated physics problems usually, such as neutronics, heat transfer, fuel performance, and transient analysis. Even within one specific physics area, many tools are available, so an analyst can kind of choose what is the most appropriate tool given the level of detail and actually accuracy required. Managing data transfer and ensuring consistency between the different computational tools is a major focus of recent developments in the reactor analysis systems. So there are a number of multi-code, multi-physics platforms available. Usually they differ in terms of what reactor types they support, what is their underlying focus. I have just 3 examples that I picked below, and I'll go through it in a sec. We developed what we call the Reactor Analysis Python driver system, and RAPIDS for short. Was developed to facilitate the connection of external codes to our Oscar 5 platform and provide a unified interface to all attached codes. So just as a comparison, I've of course not tried to include everything I can find, but the ones that are probably most familiar. So one that are probably people at NCSU are quite familiar with is Vera. So that's the virtual environment for reactor applications. So its primary focus is high fidelity simulations, and reactor type is light water reactors. The advanced reactor modeling interface is also fairly well known. So that is designed for, or was intended for, advanced reactor design. So conceptual, feasibility, and pre-conceptual design phases. Each initial design focus was for sodium cooled fast reactors, but it is now can be used for other designs as well. And then, of course, our system, which is for the Reactor Analysis Python driver system. Our primary focus is operational support, and our primary reactor type is research reactors. So just a little bit of Oscar development history. So originally, Oscar 1 and 2 was mainly a platform used to collect a number of tools from the WIM citation chain. Only in 1998, Oscar 3 was released as a full suite of in-house developed codes. Where all codes in this suite was our own codes. And it was also then established as an operational support tool at a number of research reactors. I'll get to what reactors are using the code in a sec. In 2009, Oscar 4 was released, and that was deemed a modern state-of-the-art Nodal solver package for research reactor support. We essentially added features that is required very specifically for research reactors, in particular fuel components that move, coming and going of irradiation, the fuel irradiation rigs, etc. In 2019, Oscar 5 was introduced a multi-code platform to enhance the current capabilities and support and improve support for new research reactor designs. Of course, newer trends in design are quite different to what they used to be. So the designs are look different, and so we had to make some adaptations. And of course, our plan is to include multi-physics support and also support for power reactor designs, in particular light water reactors and small modular reactors. This is a focus for us in South Africa because we have 2 operating units at the Koeberg power plant. And there is a noted interest that we continue to include some nuclear energy in the energy mix, and particular focus on SMRs. So we have some local users and collaborators within South Africa itself. So of course, Nexa is our host institution, and the code Oscar Oscar code is used as operational support tool for the Safari 1 reactor. A number of local universities we are collaborating with, so Northwest University, University of Pretoria. Entech is an engineering company that we're also in collaboration, have some collaboration agreement with. This is particular for system code integration. Our international user base, so NRG, which is in the Netherlands, They're probably, them together with TU Delft, the next one, are our oldest users. They've been using the system since late 1990s. At NRG, which is the site in Petten, it is used for operational support of the high flux reactor. We also have a number of collaboration projects with NRG. At TU Delft, it is used to support the Hoger Onderwijs reactor at the university there. We have some agreement with Pallas. That is the new reactor that is being designed and built in the Netherlands. That was for initial design evaluation. The work was actually through NRG because Pallas did not have capacity at that point. We also have some collaboration with McMaster University in Canada and support their reactor, so the McMaster nuclear reactor. Some initial collaboration agreements with ANSTO in Australia, and of course NCSU, North Carolina State University. We have a grant agreement that is in particular for our use of CTF, and of course to help develop our power reactor support capabilities, and some collaboration agreement with INVAP, which is a major research reactor designer based in Argentina. Okay, so now I'll start introducing the Oscar platform itself. So I would make just a quick list of all components that is currently in the system itself, and all the components that were planned at some point to be inserted or scoped, and all the ones that are under development. So this is a kind of a complete picture, and I try to clearly say which are truly in use and which is still under development. So Rapids, of course, we've already kind of introduced. So that's our Python-based pre- and post-processing platform. Of course, it covers multiple areas, and this is our primary interface to the entire system. McRack is the multi-group nodal diffusion solver. Its primary area is Neutronics. It's an in-house code development. Compose is a system really built upon Rapids. So it's called the Oscar model preparation system that is used to prepare homogeneous cross-section libraries. Serpent is a Monte Carlo code developed at VTT Tech in Finland. So that's for neutronics and radiation transport. It is not our code, but we have an adapter for that code. So it's an adapter to external off-the-shelf code. The same was with MCP, which is probably most people are familiar with. Heerden is a 2D collision probability lattice physics code. This is an in-house developed code. Condor, also collision probability. It's developed in collaboration with INVAP. Cogent is kind of our new developed transport code. It's called the coarse-grained particle transport. In-house, it is currently under heavy development. Enjoy for nuclear data processing. We have some touch points with Enjoy. VSOP, originally it was scoped as part of the new project sponsored by a utility, but it is paused since that project was cancelled. VSOP also now has a new form, which is called HCP. Tabasco is our in-house developed basic subchannel code for pin-type fuel. The thermohydraulic code. OTA, same for plate-type fuel. Phoenix, subchannel code that we use that is tried to connect to the system in collaboration with VTT. It is the subchannel code that I believe is used within Serpent itself. Cobra TF, of course, a major collaboration with North Carolina State. CTF fuel, this is a kind of a new development. It's something that we would like to look in the future as also attaching to the system. Relap, kind of well-known system code. Also an adapter to external off-the-shelf code. This is also still under development. Flownex is also system code. This is a South African developed code. We are developing this connection in collaboration with MTech. This is a good code or a good candidate for us because they have a kind of a niche in SMR because they are very geared towards gas flow, also for high temperature reactors. YAID is a discrete element analysis tool that is used for dispersed particle distribution and gravity deposition simulation, typically for Pebble bed type reactors. Okay, so how all the components fit together. So this is kind of a busy slide. Let me try and explain what is going on there. So the central part of the entire system, so blue components are part of Rapids with the pre and post processing platform. and individual code components are these ones in dark orange and light orange. Purple means they're the connections to codes, and dashed means it's under development or development was paused. So the central part of the system is the building of a unified model. Unified here means that the model data is input in a code independent language. It's built within the language of Rapids, so that it's not particular to say a specific target code like MCMP or Serpent, but it is independent. And the flow path here, it denotes the flow to actual target code. So if you start with a unified model, which is really built from a bunch of 3D heterogeneous components and then combined into a reactor model, if you go this way, then you will get to your, there is usually a simple translation, because the unified model, the geometric detail is quite fine. So there's a relatively direct translation to codes that can handle this level of details. So codes like Serpent and MCMP can take input directly from this model. Usually, if you want to use homogenized solvers like McCrack, which is a nodal diffusion code, you need to go through some homogenization process, and that is what the composed system is about. So I'll have a little bit of I have an extra slide giving you a little bit more detail about the system, but that is what we use. That is what we use to prepare homogenized libraries for nodal codes like McCrack and BSOP to some extent. And of course, here you have all your lattice codes and codes that prepare homogenized cross sections. So this is the kind of the data flow. Oops. This is the data flow or the model data, how the model data gets added to the code. And this is the application flow, so what the model is being used for. So in between these are a bunch of utilities that help with the deploy process. So for model deploy, we have some 3D visualization to check geometry. There's some geometry processing, so mesh generation, etc., and also cross-section management. And before going to an application, we have application input data processing and visualization, computational resource management. So, I mean, if you want to deploy the application to a cluster, that's all handled internally. Inventory management, so your composition of your fuel. And then we get to the applications. So as we will see, and I'll get to this also in a little bit more detail later. So Rapids defines kind of a number of predefined applications for very specific tasks. So for instance, local flux analysis, core follow, core design and reload, equilibrium studies, transient analysis, etc. And then there's another translation to target code. And then finally, after the code run, you get to post-processing and visualization of results. So these little dots, usually we give this presentation and show us that the Oscar 5 platform can be used as a kind of a fit-for-purpose tool or help you decide which code to use for what task. So as an example, for local flux analysis, here the circles means the bigger the circle, the bigger the error. Green means it's a very fast and efficient for it, and red means it's very slow. So for local flux analysis, McCrack is reasonably fast, but the error associated with it is large, whereas something like Serpent has a smallish error, but it is, of course, a lot more expensive calculation. Okay, so I think I will go now into, for each of the, at least for our in-house developed codes, I have a separate slide just quickly overviewing what they are about. And most of the touch points, so for instance, the model, I have a separate section on how the model is managed, and I have a separate section on how applications are actually deployed. So the Rapids platform, so it's a little bit of more of information about the Rapids platform itself. So this is a Python-based platform that is used to connect all the components of the Oscar 5 suite and provide a unified interface. It is mostly written in Python, but some core numerics and the heavy data structures and geometric algorithms are implemented in C++ with appropriate Python bindings. It has a multi-level user interaction, so high-level Python scripting interface, which usually is restricted to keyword value pair assignments. So that is what we deem as the high-level interface. Workflow-based graphical user interface. Many of these components are already in place, but it is still under development. And then, of course, we have an extensive Python API for advanced customization. So people that really want to get under the hood. We make extensive use of modern tools. That is because Python is a fairly widely used tool. So VTK for three-dimensional visualization, PyQt for GUI elements, and then Sphinx for documentation generation. So what are the advantages of moving to a Python-based platform? So Python provides a powerful and flexible platform with many advantages for both developers and users. So Rapids can act as a static code system, but it's frequently better to view it as a framework with a powerful set of tools, allowing one to tackle a wide range of problems. So from an operational support perspective, this allows us to quickly create custom workflows that match current procedure. So that's why we typically have a long process where we work with new users to establish the system there and best match the way that they want to use it and match what they want to get out of the system. And with Python, that's just now much easier to do. And that codes that are already an integral part of the calculation support activities can be integrated to the platform. And then from a research or reactive design perspective, any parameter in the model can be easily perturbed, making it easy to perform parametric studies and large design sweeps. And it is also well positioned to make use of or interact with cutting-edge Python data science tools such as machine learning. A little bit more on McRack. So McRack is a nodal diffusion code applying multi-group analytic nodal method to solve neutron diffusion equation. It uses general equivalence theory to minimize errors, utilizes pre-tabulated homogenized cross-sections at various state conditions. Flux reconstruction is implemented to recover pin level fluxes and powers. Supports rectangle, hexagonal, and cylindrical geometries, thermal feedback models for plate and pin type designs. I'll get into a little bit more detail on this later. Steady state point kinetic and spatial kinetic solution are included. And it also has a joint solution option to help in the generation of point kinetic parameters. And then actual homogenization to allow separation of material and electronic meshes. This is very important in research reactors, for instance, where we have follower type control rods, where the follower bit is fuel that actually moves. Okay, so Compose is the system that is used to produce homogenized cross sections. So it is built on the Rapids platform. It is capable of performing homogenization calculations in complex full core environments, which is also essential for research reactor designs to capture complex X-core facilities like beam lines, etc., and complex reflector configurations. So this is a picture of the overlay mesh for Safari, for instance. And it provides a detailed error monitoring during the process when various approximations are introduced so that an initial error margin on the homogenized model can be established. Assemblies that move around, so loadable components like fuel, they are homogenized in the usual way in simplified environments and then pre-tabulated against various conditions like burn up, fuel, moderated temperature, fuel temperature, etc. Currently, most of our homogenization is performed using the Serpent adapter. So that means that we avoid many of the approximations that are usually introduced in traditional lattice codes with the fine group libraries. Cogent, I'll talk very briefly about this. So this is still under very heavy development, but this is our Monte Carlo-based transport solver, and it has some deterministic elements included as well. It's designed specifically for modern many-core architectures, GPUs. It is intended to replace our dated lattice code, Heerden, which is a collision probability code, and also lessen our dependence on external codes such as Serpent and MCMP. Early prototypes have already been used in benchmarking, but it's still very much under development. Hopefully, I will get back to developing this soon. Okay, so now I'll talk about the Rapids data model, so the unified model, how it looks like. So the data model, this is basically a diagram describing the underlying data model. For anybody that's familiar with Monte Carlo codes like MCMP or Serpent, this should look familiar. It is very similar, although there are some subtle differences. So the fundamental building blocks are cells, and they're built using a constructive solid geometry approach. So that's my cells. This approach allows for arbitrary complex geometries to be created. And then, because of, I mean, it's difficult to build most assemblies cell by cell, there are some auto cell construction using building macros. So many fuel designs are, there are macros that originally or completely build the assembly or create the cells based on a few standard parameters like fuel pitch, meat width, etc. I have a separate slide on showing what kind of assemblies can be constructed. Finally, once you have your assembly library, a full configuration is defined by combining the assemblies into a certain kind of a core layout. Various core configurations are constructed, so you can define rectangular or hexagonal, rectangular, hexagonal, or triangular layout, or a completely unstructured layout. In many of the more advanced research reactor designs, of course, the layout is not a simple mesh. And the X-core facilities are components in themselves, so that those are taken care of using the same fundamental building blocks that was used to define the assemblies. Then there is an assembly inventory, which keeps track of the fuel content or the burnable material content, or actually anything that changes within the assembly. And then there's also a facility manager, which takes care of where the assembly is. So and all these are essentially databases that are based on a timestamp. So at any given timestamp, you know what is the content of the assembly and whether it is in the vault, the pool, or in the core itself. So this complete data model is then used to, at any particular point, get the complete state of the reactor. I forgot to mention. So homogenized cross-sections, homogenized representations are stored together with the assembly. So it's attached to an assembly. So after you've run compose and you have homogenized mixtures, they are basic homogenized representation of the assembly is built and stored with the assembly so that it can be used with your coarse mesh methods. Just a little bit more on the geometric model used within Rapids. So the fine scale geometry is stored using the infinite precision number types available in the computational geometry algorithm library. So this allows us to do a large amount of geometric algorithms at high precision. So mesh generation, mesh completion in Monte Carlo. What that means is, I mean, you don't have to add every single little water cell. The algorithm will fill that in for you, so you can focus on the structure of the assembly itself. Interactive 3D visualization through the VTK pipeline, so you can explore your assemblies. Geometry and materials can be imported from an existing input deck, so it's a very, many of our users that use this way to get started. So if you have an CMP input deck, I can import the geometry, we can import the geometry, and you have a model to start with. Export to FreeCAD, it's kind of the CAD tool that we prefer because it's also Python based, which can then be used to check the geometry and help the model, prepare the model for CFD analysis if that is desired. And just a note that the X-core region is built using the same building blocks, so detailed representations of the reflector, containment, baffle, and other X-core facilities like beams and so forth that appears in the research reactors can be specified. So this is just a picture of how a model was documented in FreeCAD. So this is a real Rapids model. So what kind of fuel assemblies we can construct? So this is just an example, few examples. So plate type fuel, this is our major, large amount of our users have this kind of fuel. So MTR, material testing type reactor fuel. Just two examples, so one typical assembly and then one assembly with intra-assembly control, both plate type assemblies. Pin type fuel, so light water reactor. So there are macros to construct detailed representations of PWR fuel or dispersed fuel, so for high temperature reactors. So there are prismatic designs are implemented, and then pebble bed designs with then the gravity deposition of pebbles calculated using the finite discrete element plugin YAID. Okay, so once you have the data captured, it's now to do, how do we do work with that data? So this is the Rapids application workflow. So just a quick overview first. So Rapid defines a number of predefined applications with specific purpose and set of outputs, expected outputs. Or applications are based on a common framework, which makes it easier to add new applications or modify existing ones. And most applications can be performed with any of the supported physics code. So thus, if with a single input, it is possible to run the calculation with two codes. So you can run it with MCMP, and without changing the input, you can run it with McRack. So this makes it also a very convenient tool for verification type exercises. Support executing and monitoring of application runs on the remote machines, such as remote clusters. So that means Rapids acts mostly as a client, and we communicate with the remote machine, sending jobs there and monitoring them and then getting them back. And then only the target code, so for instance, MCMP needs to be installed on a remote machine. So the entire Rapids infrastructure does not need to exist on the remote machine. So what is the application interface? So application input is specified using Python scripts, which in most typical use cases only require like setting a few keyword value pairs. Applications can be executed using an extensive command line interface, in a terminal. So this is an example of how a typical command would look like. Alternatively, applications can be launched directly from the Python interpreter or a notebook session. I see that unfortunately my Jupyter session picture didn't make it. I'm sorry. An interactive GUI-based launcher is also under development. So there are a number of options to interact with the system depending on your level of familiarity and comfort with Python. So how how data output from applications are extracted. So application output is stored in very application-specific binary result files. There are a number of ways to view this. So application-specific result viewer GUIs. Use of the Python interface. Again, if you're an advanced user, you can open the objects directly and explore them using Python. And then we also have an automatic documentation system that allows you to include output values directly within a document. So the documentation system facilitates the inclusion of output variables directly in the document. I just said that, but it is based on the light markup language restructured text. And that can produce, and then through the docutils utility, which is also a Python utility, it can produce HTML and PDF and docx format. So this is a little bit of an example, but typically your workflow you would then write most of the skeleton of the document, and then a few directives and variable tokens that would then be replaced with the results as they become available. This is a feature that is you can use to combine many application outputs into a single document, but this is also the main tool we use in applications that generate a report as part of their output. As we'll get to some of those examples in a sec. So a few examples of application modes. So first example is just a basic, what we call a critical case. So this calculates the snapshot equilibrium fission source distribution. And of course, any response that you want from that calculation as well. So typical input timestamp, as I said before, this is what tells the system what the state of the machine is. Additional model state, such as controller position, and of course, many other parameters that you would need in such a snapshot calc. And typical outputs, K effective, of course, your power distribution, your flux distribution. And this is just an example of a flux distribution in the X-core radiation facilities for the Opal reactor in Australia. Of course, criticality calculations are not restricted to the reactor itself. So it can also be used in the assessment of other facilities, so spent fuel, frost storage vault, or fuel manufacturing plant. Actually, Rapids is fairly well suited to this task because it's flexible, and the data structures allows any component to be changed, and it is useful because in many criticality calculations, various accident scenarios like various levels of moisture incursion, etc., needs to be examined. So this tool is actually very useful in those situations as well. Next example is a typical core follow calculation. So this main intent of this calculation is to update the fuel inventory by burning through an operational cycle using available plant data usually. So typical inputs is when the cycle starts. This is again to recover the state of the reactor at that point. Irradiation history, so what happened during the cycle, the power levels, bank positions, poison levels, etc. The application can also treat the explicit movement of fueled and non-fueled targets during the cycle. So if you include irradiation rigs and they move through the cycle, I mean, they can be treated explicitly. Typical outputs is, again, effective multiplication factor trending so that you can estimate your model bias, because usually these K effectives are compared to real plant state, so they should be close to 1. Updated fuel assembly inventory, of course, and a few other parameters are usually exported as well. User customizable reports can also be produced as part of the output. And for most of our users, this typically includes reactivity plots, power maps, and then inventory reports. So you get at the end of each cycle, you get a snapshot from what is in your pool, what kind of fuel assemblies are in your pool. So next example is a reload. So this is for the performing predictive calculations for the coming cycle and check safety and utilization parameters. So typical inputs here are the candidate loading, number of predictive lines, which would form an envelope for conditions during the cycle. So especially in research reactors, there are many things that can happen during the cycle. You know, some production loading or radiation rig loading might be slightly different. So many predictive lines are allowed so that you can get an enveloping condition for the coming cycle. And then, of course, you ask what kind of parameters to check: excess reactivity, shutdown margin, peak power density, etc. This is a fairly complex application mode, which usually creates many additional cases, sub-applications internally, depending on what is required. And the output is usually summarized in a user-defined report, so using the documentation system. This is some examples of like a summary table of some of the parameters calculated using this mode. Okay, next example is the sampler application. So this is a general framework used for uncertainty propagation following a total Monte Carlo approach. So it is a generic kind of a framework, and so it has very many customizable components. So basically it takes as input a variable space defining what should be perturbed and how they should be sampled, how the variables perturb the underlying model, what application should be run during the iteration process, and then the output parameters on which uncertainties should be accumulated. So default objects exist, which samples uncertainties already available in the model data, so cross-sections, geometry data, if they were captured, and automatically create applications based on requested responses. So yeah, this is also, looks like I have a slightly older version of the slides. Okay, this is an example of a sampler used in a real study that was to determine uncertainty propagation through relap. And then basically a relap input deck was created and output was extracted from that relap deck and accumulated. So this is, next one is, and this is the final example I have, is multi-objective optimization. So general framework used to drive multi-objective optimization problems. So it has as input a design space defining target values that should be perturbed, how the target values perturb the underlying model data, what application should be run during the iteration process, and then the constraints and objectives based on output parameters. So what do you want to maximize or minimize, and what are the specific constraints? So the particular design space related to cycle in-core fuel management has been studied quite extensively. So the approach employed an amalgam hyperheuristic to tailor the optimization algorithm for this particular problem. Certain surrogate models, so models produced using machine learning techniques such as artificial neural networks, may assist the optimization studies by rendering the evaluation of different combinations much, much faster, instead of relying on running a particular analysis codes for this purpose. This is the focus of PhD work jointly supervised at NCSU and Nexa. Some other applications, so there are many more modes available. I don't have time to go through all of them. So some honorable mentions, so equilibrium. which runs depletion calculations using a specific specified reload strategy until a equilibrium mass distribution is reached. Rodworth calculation of reactivity feedback tables, transient simulations, and many others. The Python also interface is also very convenient and or powerful, and allows an experienced user to then create custom workflows by combining existing applications. So it's not really restricted to the applications in here. I mean, they can all be combined in various ways to create new kind of applications. So moving to our current status on multi-physics support. So of course, critical to the success of any multi-code multi-physics platform is the development of plugins so that physics codes and capabilities can be added. So this is just a diagram describing the Rapids approach to the plugin system, to physics plugins. It is based heavily on a template engine, and we use the Cheetah template engine. So it is fairly optimized for creating input, although the template engine can also handle in-memory plugins developed directly in Python. So I/O is not strictly required needed, but it is probably best, most optimal for plugins that would require input writing and output processing. The plugin mechanism currently allows for a granular plugin development, but it's optional, as I will explain in a bit. So you can start by developing templates that produce code inputs for each and every single individual data element. So your geometry, materials, radiation history, etc. And then finally, they are combined and then to get the model into the application template. But this stage can be skipped. So if you, say, want to use a complete deck without building the individual data elements themselves, only a very specific application template needs to be developed for that. And that, for instance, in that sampler application where we were driving or running a relap, this is the case. So we did not write the entire relap input deck, only had a few touch points, and that was our application input template. Then there is, once you have an application template, you can create the code input. An execution template tells us how the code should be executed. Once the code is out, code is produced, a recipe tells the system how to interpret the output and feed it back to the application. These recipes are usually based on a set framework, so you know exactly what are the things that the code needs to give you. Okay, so just onto the different areas of physics. So first, Neutronics. This is, of course, our strength. Our primary users are research reactors, and Neutronics are very important there, or more important than certain other physics. Just a few topics in our current support of them. So particle transport. So our plugins for Serpent and MCMP are very mature, so that large input decks for these codes can be created automatically from the available model data. Most application modes are supported through Serpent and MCMP, especially MCMP 6, which now, of course, can also perform irradiations. So the support for these two codes are quite mature. Use of diffusion codes. So we fully support our in-house developed multi-group nodal diffusion solver, McCrack. Other diffusion codes can be added through the plugin mechanism. For instance, the homogenized cross-section data is stored within Rapid structure itself. So it's not so difficult to extract that and to write libraries for other nodal or other diffusion solvers. Nuclide data. So Rapids has internal structures to store detailed transmutation chains from raw ENDF data. Decay and transmutation solvers are also available. Cross-section data, basic support for pointwise and multi-group neutron cross-section library formats, both in the generation of them through Enjoy and then just basically storing, visualizing them, etc. Uncertainty propagation. So model uncertainties are captured in the model data, and cross-section uncertainties are captured using the mechanism available through Tally. So this is still under development for the cross-section bit, and that's a collaborative project with NRG in the Netherlands. For thermal hydraulics, this is a semi-new area for us, although some work, of course, has been done. So for non-communicating subchannels, we have simple assembly average thermal feedback through the plugins Otta for plate type fuel and Tabasco for pin type fuel. We're also working on coupling to Phoenix as well as Cobra TF. We've been working for quite a while on that, but I think we're finally going to make some progress. So, but that is still under development. Detailed multi-channel. So this will be part of the link with Cobra TF. And just a note that the detail available in the model data also makes it possible, if required, to interface directly with CFD codes using the plugin mechanism. So for transient analysis, so kinetics parameter generation, so we can extract and store kinetics parameters from any attached physics codes that support this calculation. So these include McRack, Serpent, and MCMP. Calculation of reactivity feedback tables. There are dedicated application modes specifically for this purpose, so you can create quite extensive feedback tables, Rodworth tables, etc. System code integration. So as I mentioned before, using the template-based mechanism, any existing system in code input deck can be easily adapted so that the core sections can be written using using the data available through the solver. So kinetics data feedback tables. Capturing of the system data is actually an important development area for us. So just like we capture geometry in a code independent way, we are developing the system model representation in Rapids itself, and then deploying that to system codes such as Relab and Flownex for then full system analysis. And then you have, again, kind of tried to create a consistent model with the Neutronics model. So spatial kinetics and 3D spatial kinetics. So we have application modes that can drive transient simulations through attached physics codes that support this feature, in particular McRack or in-house code as a 3D kinetics option. So a little bit on quality assurance and the current VND status. So co-development and the release procedure. So our development is based on internal procedure documents based on South African nuclear regulatory requirements. Change control. So all our code sits in Git repositories, and the repositories are hosted on private access controls, GitLab accounts. Access is available for development partners. Testing. So we have a set of unit tests and then a full integration test suite for which covers most of the benchmark problems, which I'll show in the next few slides. Testing is automated using the robot testing framework. So the process of running through all these tests is automated. Distribution. So we've embraced the multi-platform package manager Conda, because most of the package is now Python, but it also includes other stuff. So for instance, the solvers is not necessarily Python, but Conda is flexible enough to cover the distribution of these as well. And it can be installed using Anaconda, but self-contained installers are also available, which then contains all the necessary components. And another nice thing about Conda, it is multi-platform. So we support Windows, Linux platforms. Documentation. So the comprehensive HTML documentation is available as a separate HTML package. Same for the target code specific documentation like McRack. And of course, online hosting of the documentation is planned for the near future once we have the correct platform identified for this purpose. Training and support. So the code system ships with a number of training tutorials. We have workshops. As you can see from the timeline, our workshops are about a decade apart, but we plan to increase the frequency of these. The benchmark sets, as I will show in the next few slides, can also be used as advanced training. And then we're also planning on adding additional material such as videos, tutorials, and a proper user forum are planned for the near future. So this is just some examples of the user documentation. So verification and validation status. The validation is based on a set of full reactor benchmark problems. So many of these benchmarks were developed during 2 IAEA coordinated research projects, CRPs. They present a reasonable spread, at least amongst research reactors, of core, fuel, and control design, reflector choice, use of burnable poisons, power and burn-up levels. The validation cases can be supplemented with code-to-code verification cases. As I mentioned before, the multi-code approach is particularly suited for this task because same application can be run in 2 codes. Verification and validation cases are run as part of the integration test suite. So that we see as the highest level of testing to have a full validation suite. So Rapids also includes a validation framework, which allows cases to be mapped to specified set of physical phenomena. And then the validation results are track of the validation results are kept in a centralized database, so that the snapshot of the performance of any code can be recovered at any time. Then the validation framework also interacts with the documentation system itself, so that validation matrices can be automatically pulled into a comprehensive V&V report. So I'll quickly go through what is in our validation database. So what kind of models, what kind of reactors have we modeled? Most of these include detailed experimental measurements. So this is real experimental comparison. We have a benchmark version of the Safari 1 reactor, which was developed for the second IAEA CRP. Primary area is Neutronics, and topics include fuel burnup and beryllium activation. ETRR2 is also MTR, Egyptian reactor, Neutronics. There's also some transient cases, so control rod induced transients, and fuel burnup measurements as well. So Opal is also MTR, Neutronics, fuel burnup, material activation. What makes Opal a little bit different than the other two is that this is a heavy water reflected reactor with a very, very small compact core. INR is a modified trigger pin type fuel reactor. From what we've seen of Pulsar, this I think is fairly close or similar to what the Pulsar reactor is. Also Neutronics, there's the particular example there involved fuel sample burnup, a fuel sample burnup experiment over multiple cycles, so fuel testing. Israeli research reactor, so MTR, Neutronics is for fuel burnup. This is a nice benchmark because it includes like burnup measurements of well irradiated fuel. MNR, McMaster reactor, so initial benchmark developed. SPIRT4, Neutronics, Transient Analysis. IPEN, zero power facility for fuel sample activation. These two are fairly new to the set, so AQR2 and Crocus, those are both zero power facilities. The Neutronics, but for transient analysis, and both these are experimental facilities involved in neutron noise experiments in the greater EU Cortex project. So that's for noise detection. So this is one of the two of the benchmarks that we use for 3D kinetics verification or validation. So on to now non-research reactor models. So we have initial models for Beavers and for Wattsbar. But it's important to note that as we're still in the process of improving our thermohydraulic feedback, we're still in the hot zero power cases, so mostly reactivity tests and so forth. And then we also have some initial high temperature reactor models built, for which there are some specifications, because those are on the rare side to have good specifications. But the HR10 model, we have some initial, HR10, we have some initial model in the validation set. Okay, so on to the concluding remarks. So since the bulk of our current user base is in the research reactor community, I mean, their needs will continue to shape the system's development in the near future. Multi-physics support is, however, currently of interest even within this community. I mean, I think this is a general trend within all reactor analysis communities, is to improve the fidelity of our models. And of course, then the inclusion of thermal hydraulic feedback is kind of a natural next step. And there is a upcoming IAEA CRP, so a new one, which is starting in 2022, which intends to focus on this topic, and we will plan to be heavily involved. So this is another kind of accelerator for us to improve our multiphysics. Support for LWR and SMR designs are also high on our priority list. As I mentioned, we do have some drivers within South Africa for us to ensure that we can support these types of designs. Although Oscar has been used in numerous student projects, we believe the current platform also provides new opportunities for research projects and collaborative development. So the new platform is a lot more flexible than the older ones, which was basically built around the Nodal solver itself. So there are lots of untapped potential, we believe. So I note here that our current grant agreement with NCSU facilitates the use of OSCAR 5 for academic purposes at NCSU. So the code is actually available for use at the university. An OSCAR model of the pulsar reactor would also be a good introduction to the system, and work towards this end based on an initial set of specifications, very basic specifications, has already started. And I think that is my spiel. So questions?
Well, thank you very much. This time, I guess we'll open the floor for questions. As usual, we'll have questions on both the chat and then people can raise their hand and ask them themselves if they'd prefer. Either's fine. If they're on the chat, I'll go ahead and read them off for the recording, and then we can answer them from there. So with that, we have our first question on the chat room. The question is, you have mentioned the implementation of the discrete element method for the packing of fuel particles or pebbles. I was wondering if this implementation also allows for the granular flow of pebbles while performing neutronic and thermohydraulic calculations.
So yes, so the Yade system is a dynamic system. So I mean, you can get an initial deposition, and then you can start flowing the pebbles, right, as you open up, and it is exactly used for this purpose, to move discrete elements through a system and manage their physics interaction. It is of course not very fast, so this will really slow down your simulation. It might be something, but it can be done online. I would say it is much more feasible than it was, say, a decade ago. But this might still be something that you would do as a once-off process to establish proper flow lines through the core. But definitely it is dynamic. So it can do initial deposition and then also move the pebbles through the core.
Excellent, thank you. We have a second question on the chat. Will higher fidelity computational fluid dynamic code be adapted into OSCAR in the future, such as NEC 5000, for example? So
we have not. So our only interaction with CFD analysis is through exporting it to something like FreeCAD, and then somebody else doing the meshing and doing the CFD analysis. So we have not directly looked at the set points of how this can potentially be done, but we know that there is enough data there. So we have, because many CFD analysis with our models have been done for heating analysis of samples, etc. So the data is there, but we have not explored as a particular CFD code.
Thank you. Next question is that you showed smaller errors for Cogent than Serpent and MCMP. Dr. Asney believes they're smaller errors than what those two codes have shown. Can you explain how that is?
Yeah, one of them might be a misinterpretation of me of the dots, but I think one of the reasons I might have made a difference is especially in terms with Serpent. So Serpent has a collision estimator only. Actually, now I remember. So I did make it smaller than Serpent and MCMP because Cogent automatically uses a exponential attenuation method on its tracks. So it has a fairly good coverage through thin regions. Right, so there is when tallies are calculated, it's calculated the entire track with the weight attenuated along the track. So I think it is similar to the exponential attenuation method that is available in MCMP as a variance reduction method, but that is implemented, that is the base way of how the code operates.
Okay, an unrelated but follow-up question from Dr. Asney is curiosity over where the name OSCAR came from.
So OSCAR stands for the overall system for the calculation of reactors. So that's what the acronym stands for. It kind of has a phonetic interpretation in Afrikaans, which if you pronounce it in Afrikaans language, it is read as Oscar, which is it translates roughly to something pulled by an ox. So it's kind of like a workhorse. Yeah. But the acronym stands for Overall System for the Calculation of Reactors.
Thank you. Any more questions from the audience? Either post it on the chat or feel free to raise your hand and ask. I'll call on you. What time is it over there right now, Francois?
1 minute past midnight.
Man, okay. Well, thank you very much for staying up late with us. We appreciate it.
No problem.
Well, the good news is that you can get to bed because it doesn't look like there's any other questions coming up at this time from the audience. I'll give it the usual going once and going twice. And I don't see any other hands coming up or anything else getting posted on the chat. So at this time, I would like to thank you for staying up late with us and giving us a great presentation and fielding our questions. And hopefully look forward to seeing you face-to-face sometime in the near future. So thank you very much for your time.
There's actually one more question.
Oh, there is. Something just popped up. Okay. So the follow-up question that just came up in the chat, would your code allow for the tracking of a single pebble?
Yes. So you can mark the elements, so you can see how one moves. Yeah. So you can track where it goes. So, but I mean, this is, I must stress that this is a kind of an off-the-shelf code. So Yade is a Python-based system, so it is not our code. It's just incorporated to help us with the dispersed particle distribution. So gravity deposition, but also other kind of dispersed distributions. But yes, it can. Yeah.
Thank you.
Thank you, Francois. And thank you to Nexa and the group. And looking forward to our continued cooperation.
Oh, thank you, Kosterin. Thank you for the opportunity, and best of luck to you guys.
You too. See you soon. Thank you.
Yeah, bye.